On this episode of the Cyber Gizmo, I'm going to be talking about how do you know you're getting all the performance that you paid for when you bought your new NVMe drive. How do we measure that? So one of the famous quotes is, "My storage device has all the storage I will ever need." No one has ever said that. We're going to pre-flight. So I guess the question is, why would you want to pre-flight and check over your NVMe? Well, there's a lot of things that can go wrong with an NVMe. And there's also a lot of different configuration options on whatever machine you have. For example, the Intel machine that I have has 2 slots for an NVMe. Both of them take 2280. One of them is PCIe 3. The other one is PCIe 4. Get the wrong one, you cut your bandwidth in half. The other problem that can happen with NVMe's is the pins can get dirty. And if that happens, you could have problems with the signaling on the drive. It may look perfectly fine, but you may find that you're taking a lot of errors, or maybe you don't know you're taking a lot of errors, and the drive gets slower and slower and slower. And there are utilities that will tell you a lot that's going on. Let's just assume that we bought it new. Now I did, and I'm actually checking mine out. Even though I've done some benchmarks on it, I'm not too sure it's performing at the right level. So let's find out. And how do we do that? I'm on my Proxmox machine. I'm sitting in a command prompt. There's some utilities that will help you identify information about your NVMe drives. So the first one is the NVMe command, and that one usually is not installed by default. It may be on your distribution, it just depends. I'm using Debian here because that's the base operating system for Proxmox, Debian 12 actually. So we can look for it. And you'll find it right here, nvme-cli. And that has the command that we actually want to run. So what do we need to do? The only thing that I want to do is, you can see there's just all kinds of commands. But for me, I just want to see all the NVMe devices. So NVMe list, and then we'll do a verbose to get any additional information. As you can see, this is a pretty wide format. We'll stretch it out a little bit so we can actually see it. You have the device, which is NVMe 0. NVMe 0 is what makes up your namespace. So that becomes part of the drive name. So this is the firmware. This is the transmission port. And then we have the address, which is 0000100.1. So that's the PCIe address. So that part we're going to need to know in the next part of this. So the next thing I want to do is an ls. I want to inquire the PCIe bus. And we're going to go after a verbose mode, and we're going to do -n, then -s. And this is where this comes into play. I'm just going to type it in, maybe. Now, the only part of this I need is the LNK, or the link information. You can, here's the whole thing. You can see that there's an awful lot of information here. I'm not going to go through all of this, but if you're interested in it, you can go through the LSPCI manual. So that's why I only need this much. So the thing that we're looking for is, first, what is the capacity? What am I plugged into? Am I plugged into a PCIe 3 port or a 4? I got it right. It's the PCIe 4. So because it's showing a speed of 16 gigatransfers per second. If this had been PCIe 3, that would be 8 gigatransfers per second. The width is the number of PCIe lanes. Typically, NVMe takes 4 lanes. And that's what we want to see. What we don't want to see is something that shows us being shared with a 16-lane bus, because that means we're competing to get our 4 lanes off of that 16-lane bus, and we're competing with other devices that are connected to the system. So we want a nice clean shot into the CPU. The link status, so that's the capacity, the capability, but the actual status is showing us that we are running at 16 gigatransfers and the width is 4. So you need both of these pieces of information. That, yeah, it's one thing, because this is where you could be limited if there was problems with the drive, a dirty connector, wasn't plugged in well, maybe it's loose. Yeah, those kinds of things can cause problems for you. We need to look up what Samsung says the device is capable of. So according to Samsung's website, NVMe 990 Pro has a read-write speed of 7450 and 69 megabytes per second. So the two numbers with the slashes, the higher number is the read, the lower number is the write speed. Then they go on and they specify for random reads and random writes, that would be using 4K blocks. Now, typically, as you notice back up here, or maybe you didn't catch it, but right here it's telling you the format of the drive is 512. But you can block those up, and you can use this at 4096. You can change that number that's there. However, I will warn you, some operating systems, some Linux kernels don't react well. Yeah, so sometimes there are parts of the system that just won't react well to 4096. So experiment with it if you wish, but I just leave well enough alone. Random read and write capabilities for this drive, according to Samsung, is 1400K for the read and 1500K for the write. And that's not in megabytes per second, that is in IOPS. How do we know that this drive that I have in here is performing at the speed that Samsung says it should? That's what I'm interested in today. So in order to do that, I need to have a test to run it. Well, FIO, and you can look at it, FIO is kind of the I/O tester. It does a lot more than just doing benchmarks. You can actually run this up and do tests on your drive. You can also test it in raw mode. So I could just use the raw device. I would caution you in doing that. Yes, you're going to get better information out of it. However, if you write to that and you have something already on that drive, you're going to lose it. It's gone. It's going to blow it away. So yeah, so you might want to be careful with what you're doing. I'm going to be using a file just to stay safe. So I'm going to incur some overhead for the file system, but that's okay. I don't mind. So I have some preparations here. Sequential read. You can send a file to FIO, and instead of having to write us a long command line to tell it what you want it to do, I have a global section which applies to all the devices that I'm testing. And of course, you could put, if you had multiple NVMe drives on your system, you could have it do those tests as well at the same time. So this is just a label. This is what I labeled the file, so I call it the same thing. It's time-based. There's a ramp-up time. You can make it 5, 10, whatever you want to ramp up. It just allows that, hardware doesn't react well to just hitting it with a whole bunch of data all at once. It kind of has to get things filled up in the buffers, build up all the constructs that it needs in order to actually start working well. So the ramp up time gives the hardware and the firmware time to set up and construct everything that it needs in order for this test to show performance in its best light. And that's what we want. We're not trying to crush the drive. We want it to run for 30 seconds again. If you want it to run for a minute, that's fine. Make it a minute, or 2 minutes, or an hour, whatever you want to do to see what your results are. This is your what are we going to run? We're just going to do a sequential read. So sequential read is just read. Sequential write is just write, and then we have a block size 256K. I'm doing a file size of 512. I can tell you that when you're running for any length of time, whether it be a minute or 2 minutes, if you make this file size larger, you're going to run into problems where the operating system is going to start queuing, and then you're going to see a lot of I/O waits. So if you get the file too big, you're going to build up I/O waits. That's going to affect your performance numbers, and you don't want that, right? So then you have I/O engine. This is libaio direct. That means that we're not going to use any of the Linux magical buffers, which we don't want. We don't want it to taint this. We're interested in the drive. I'm not interested in testing memory to see how fast that is. I'm interested in how fast the drive is. And so the number of jobs, we're just going to do one. That just means it acts like there's one user on the system. You can throw more at it if you want. I/O queue depth, or the I/O depth, is the number of I/Os that you can. The way this works normally is the I/O depth is set to 1 by default. Well, that means that I have to wait for the hardware to complete the write or the read before I can issue the next one. By setting my I/O depth higher, I can take advantage of Linux's parallelization and just push 32 reads at a time to the drive and then wait for them to complete before issuing the next. So that's all it's doing. And then I am giving this a file name, junk file. Now, if you're going direct to the device, you don't need to specify a size. It knows how big the device is, but if you're using a file, you do. So there you go. So let's go ahead and see how well this works. Now, this, by the way, this system is running. It has active virtual machines up and running on it, so I don't have sole use of the NVMe. Just telling you that. So I'm sharing it with the other and the VMs that are running. And there are 6 of them that are currently in operation right now. One of which heavily writes and reads to the file system. So it did a 5-second ramp up right here, and now it's starting the job. And it's counting down for the 30 seconds. So it's 6, 5, 4, 3, 2, 1, and it's done, hopefully. So what part of this are we actually interested in? There's a lot of data here. I'm not going to go through all this. There's a manual. There's a site for a file that will go through all of that. I'm not here to teach you how to use file. I'm here to just take the data and run. So this is my aggregated reads up here. So I had 27,000 IOPS, and this is the number that corresponds to what Samsung said I should get. So remember, it was 7450. Well, I'm at 7103. That's not too bad. It's pretty close. For a system that's busy, it's amazing I'm getting that much, actually. So yeah, all right. So what about the random part of this? So in that case, I also have a control file for that. And it looks like this. So in this case, we're doing the same thing. Ramp up 530. This time it's random read. The block size, we're defaulting it to 4K because that's what they're saying their random read and write tests are performed with. So I'm matching up to what their spec says to use. And the file size, again, is arbitrary. You can make that what you want. Just remember, if you get much larger than that, you get up to a gig, you're going to start seeing I/O waits, particularly now because there are 16 jobs that are hitting and building files. So yeah, just be careful that you you will affect the performance of the system if you get into an I/O wait situation, because the kernel will just stop the IOs until that IO wait clears. And so, yeah, we don't want that. We have an IO depth of 16. So why didn't we go to 32? We want to match the number of jobs. And so we want it to complete the writes, because it doesn't do us any good if it doesn't write it to the drive, right? Okay, so let's see how we do. This is just a read. This is not a write. Same thing, we're queuing up. Now we're starting to run. Again, it starts to count down. So we're just going to sit here and hammer it for 30 seconds. You can already see that it's in the ballpark. You can see it's at 1402. And it said it would be 1400. Okay, IOP. So you can already see it's... But you can see also when the other VMs are writing, because it drops when that happens. So ideally, you want to be on a system that's quiescent, but I don't want to do that because I'm capturing information. But it bullseyed at 1400K. Even though I have a system that's busy, it's still bullseyed it. So that's exactly what we'd expect on. Okay, so what we're going to do next are the two write tests. I need to do a sequential write and I need to do a random write. So let's take a look at that file again and see what we got here. We'll look at the sequential write first. And it looks pretty much like the sequential read. It's using, except for the read write is now write. And so that means sequential write. And I'm doing the direct one, number of jobs 1, IO depth 32. And I am writing to a file because I don't want to blow away the drive since Proxmox is installed on this. That would be very bad. So again, remember this drive is in use. So we're going to pause for 5 seconds and then count down to 30 and see what we get. So right away I'm seeing 64 megabytes per second. So hopefully this will come close to 68. We'll see. Okay. Same thing. We want the aggregate. It's up here. And we can see that that's the block write. We want this one. 6731 megabytes per second. And what did Samsung say? I think it was 6800. Yeah, 6800 on the right here on the sequential write. So yeah, we're in the ballpark. That's pretty close. Let's take a look at the NVMe random write. I made this one. I just took the sequential write and just changed the read write to it. So it has the same parameters. We're using 4K block sizes. It's a 512 meg file. Number of jobs 16, IO depth 16 as well. So let's just go ahead and run it and see what we get. 5-second ramp up and then a 30-second countdown. And I don't think it did. So go back up here to the aggregate again, and the writes are, the IOPS is 1569K. And Samsung said it should be 1550. So we're really, we're a little bit over there. So, and that's all I had for the write. I think that's all I think that's it. I mean, I know that I have done my pre-flight. Now, if I want to, I can go ahead and benchmark this drive because I know it is performing close to the speed that the manufacturer is saying that the drive will obtain. So I wanted to thank my Patreons and my channel members. Thank you so much. I sure do appreciate you. I'm glad that you're here to help keep the channel moving forward and going. I also want to thank you if you got this far in the video. Thank you for watching today. And with that, hope to see you all again real soon. Bye for now.